Welcome to another episode of The Power of Logic. So today I'm going to be walking through the 2022 AMC 12B, problem 25, which is the last problem on the AMC 12B. And I agree that this problem can also be an AME problem, and it's pretty difficult and challenging. So let's start to tackle it. We have 4 regular hexagons surrounded a square with sides 1. So let me just mark that this one's 1. So we have that this is equal to 1, and each one sharing an edge with the square, as shown in the figure below. The area of the resulted 12-sided outer non-convex polygon can be written as m times square root of n plus p, where m and p are integers, and n is not divisible by the square of any prime, which basically means that m root n is the simplest form. What is m plus n plus p? So now let's try to look at this problem. First, the 12-sided gon is just the bolted side gon, right? The bolted polygon outside. And we can see that this diagram is actually pretty symmetrical, right? Because of the symmetry across this line. Across every line. Across this line. Also this line. Sorry for the bad drawing, but this one is perfectly symmetrical, right? Across the diagonal line, the 2 diagonal lines, and also the horizontal line and the vertical line. So therefore, for this problem, this looks quite like an octagon, right? If we can just make up these 4. Just fill these 4 diagonal lines so that it's actually a perfect octagon. But it's not a regular octagon, right? So therefore, it's pretty easy to be mixed up. Now, how do you prove that this octagon is an equal angular octagon? Well, let's draw a line from these vertices to one of the vertex. Then let me zoom in. This is a right angle, right? And this is actually equal to this because of symmetry, right? We can actually use a lot of symmetry here to help us solve this problem because of this symmetry, diagonal symmetry. So, therefore, this is a right angle, which basically means what? This angle here is 45 degrees. So this 45 degrees. And this triangle right here, let me just color it here. This triangle is actually an equilateral, no, not equilateral, but an isosceles right triangle, right? And we also see that this is also a right angle, right? Because this is also equal to 1. So this is a right angle. So therefore, we can prove that all such angles, this kind of angle is 135 degrees. Right. So therefore, by symmetry, these are all 135 degrees, which is just an equal angular octagon. So therefore, we can actually write the area of 12-sided gon. Just zoom this in. The area is actually equal to the area of the octagon minus the blue triangle, right? Since by symmetry again, these 4 triangles, they're equal in area, right? They're equal in area, so therefore we can just multiply the area of the triangle by 4 to get the total area that we have to subtract out. Now first, we have to calculate the area of the octagon. So let me just zoom it in. So the area of octagon, we can use the same logic here, right? Extend these two lines, let it meet at a point. Then this is actually an isosceles right triangle. This green area is a right isosceles right triangle. And so how is this going to help? So the thing to possibly notice is that we can find this entire length, right? We can find the entire length. And how are we going to find this length? So this one we have to use a little bit of a combinatoric terminology. So basically, in this case, we have two hexagons, right? Two hexagons. No way, sorry, it's the wrong direction. We have two hexagons. And this is a square in the middle. So this one's 1. And this one is pretty easy to calculate. Because the side length of each of these hexagons is 1, then we can just construct, right? We can just construct a right triangle. We get this is so the total length is just square root of 3. Now, we know that the total length is equal to square root of 3, then what is happening here is that we can use the inclusion and exclusion principle. It's also called the pi terminology, which is that the union of A and B, which A and B are sets, is equal to the number of elements in A plus the number of elements in B minus the intersection of A and B. And this one is pretty easy to visualize. This one is actually a UB. If A is the octagon, no, A is a hexagon 1. B is hexagon, also the hexagon, right? Then the intersection of A and B is the side of square, which is the part that's circled in green, right? So therefore we can just use this exclusion principle to find the total length across the octagon. So now how are we going to use it? So now how are we going to do it? And just erase everything for now. So So one of the altitude of the hexagon is square root of 3. So we have root 3 times 2. This is actually a plus b, right? Minus 1. So this is the total length of the octagon, right? No, of the 12gon. So if this is the total, then can we just say that this part, let me just zoom in again, then this part, let this part be A, this part also be A, then we can agree that 2A plus and this part is 1. 2A plus 1 is equal to the total length, which is 2 root 3 minus 1. So A is just equal to radical 3 minus 1, right? This is the length of A. Now we have the length of A. Now we also have 2A, right? So therefore, we can just find the square. The entire square minus 4 times the area of the isosceles right triangles in the 4 corners. And that will give us the total area of the octagon. So let me just clarify here, since I think it's really important to try to make it step by step so that you will not you will try to avoid make silly mistakes. So the side length is equal to, let me just change the color. Black looks kind of weird. It's equal to 2 root 3 minus 1. So area of the square, that is equal to 2 root 3 minus 1 squared, right? It's equal to 13 minus 4 root 3. Now, the area of the 4 triangles, that is equal to 4 times root 3 minus 1 squared times 1/2. 2 times 4 minus 2 root 3 equal to 8 minus 4 root 3. Now you can see that the radical actually cancels out, right? If we subtract these two, then we get 5 as the area of the octagon. So now let me just erase everything that we did. Actually, I'm not going to erase, possibly. But 5 is the area of the octagon. Now let's work out the area of the little triangles. So here, I'm going to do a little bit of angle tracing. So let's look at this part here. If I can just erase this part. I'll do a little bit of angle tracing. So first, what is this area? No, what is this angle? This angle is 120 degrees. And what is the angle drawn by a green? This is 135 degrees. So therefore, this angle here is 15 degrees. And since because of symmetry across this line, then therefore this angle is also 15 degrees. So the middle angle is 150 degrees, which is a pretty nice number because 150 reminds us about 30, 60, 90 triangles, or just 30 angle in general, since these are all special triangles on the unit circle. So their sine values are actually pretty easy to compute. So here we're just going to do law of sines and law of cosines. So law of sines, we can find one of the side lengths right here, S. Then we can find the side length here. So law of sines, for law of cosines, we're just going to find 2a squared times 1 minus cosine of 50 degrees. Since by law of cosines we have a and a, then this is theta. Then by law of cosine we have a squared plus a squared minus 2 times a times a times cosine theta. This is the law of cosine's expression. So therefore, this is the law of cosine's expression, which set it to be equal to the hypotenuse. This is actually just equal to 1 mass cosine of 150 degrees. This is equal to, I'm going to use s since I used s on the left, no, on the right. This is equal to 2 times √3 minus 1 square. So therefore, we can just cancel out the 2's. We get 4 minus over 1 minus 1 plus, no, over 1 plus √3 over 2. This is equal to s squared. Now multiply these both sides by 2. We get 8 minus 4 √3 over 2 plus √3, and then we can rationalize it. This gives 28 minus 16 √3 over 1, which is just 28 minus 16 √3. So this is the answer that we have for the area for the square of the side. So now 1/2 AB sine C. It's not law of sines, but it's like the sine area formula. 1/2 times a square. Now we have 1/2 times s square times sine of 150 degrees. This is the area of a single one, right? But we have to multiply this by 4, since recalling the original diagram, we have 4 such triangles. So multiply this by 4, we're going to get 1/2 times sine of 150 degrees, which I believe is 1/2. Just zoom in a little bit. Equals to 1/2 times 1/2 times 4 times s squared, which is just equal to s squared. So this is equal to s squared being equal to 28 minus 16 √3. So this is the area of the 4 triangles. So the area desired is equal to 5 minus s squared. 5 plus 16 √3 minus 28. 16 √3 minus 23. So this is the answer in the final form. But remember that we want m times square root of m plus p. So in this form, so p is equal to -3 in this case. Don't be tricked here, because they often like to throw this kind of trick thing here. So now we have m is equal to 16, n equal to 3, p is equal to -23. So m plus n plus p is just equal to -4. And this, I believe, appears, in our answer choice. So B is our final answer. Thank you for watching, hope you enjoy, and see you next time in my next video.